is speaking behind the screen. I'm just going to turn on my background video. Yeah, so let's get started. So the other people who will come in a bit later will just, watch the earlier bit of the recording. So I've got Shakira and Akila, yeah? So Akila, you've gone through the practical exam a few days before, just for the information of the other people who have yet to sit for the exam. So Akila, did you sit for 3.3 or 3.4? Or was it 3.5 or 3.6?
3.3.
So I know in the paper 3.3, the first question was on acid-base titration, am I correct?
Yes.
And it was a slightly easy question, but it was HCl and H2SO4 and also NaOH. So the tricky thing there really is the mole ratio. So when you're dealing with this 1:2 mole ratio, make sure that you can do, mole ratio. I don't know what they want you to find, but based on mole ratio, I always label the mole of something over the mole of the other thing. Look at the balance equation. It's 1 mole of the H2SO4, 2 mole of the NaOH, and then whatever information on top, whatever information at the bottom, just remember that C times V there. This is in mole per dm cube, and your titration most of the time will be in cm cube. So you need to convert that into dm cube, not cm cube. So you need to convert that, yeah? So I think apart from that, that was all right. The biggest issue I've heard of was the use of this thing called thymolphthalate. That was your indicator, am I correct?
Yes.
So for, I don't know, Shakira, I really don't know what practical is going to come out the next time, yeah? But this is the practical syllabus for the 2022 exam onwards. And it's mentioned that a couple of, we can read through the rest of it. I'm just going to go straight to the list of practical. So these are the list of practical on page 57. So this is page 57 of the syllabus. So quantitative analysis, titrations, as expected, use a burette, do a rough. You must show a rough titration. You must carry out titration until concordant results are obtained, because each of your burette reading is to plus minus 0.05 cm cube. So therefore, you need 2 readings. So that means overall titer comes from 2 reading. That is your final minus your initial. So that your biggest maximum allowed difference is your plus minus 0.10 cm cube. So Akila, I'm not sure whether you are retaking your AS exam in November or not, but if you are, then you will be resitting your practical exam as well. So you might want to, take notes of little bit of pieces here and there, so that it might be helpful for you the next time you sit for this kind of practical exam. This is error in overall reading. This is error in a burette titer. Titer comes from the final minus initial. You needed 2 readings to give you the titer, but each reading only is plus minus 0.05. This is double that because you have the initial and the final volume. You get it from 2 readings. I was asking Akila on the indicators use because there is the use of indicators as listed on page 61. So it's not outside the syllabus. It is actually inside the syllabus, page 61. So on page 61, there is that methyl orange indicator, bromophenol, thymol blue, and thymolphthalate. So methyl orange is quite common. You know that it's orange at the end point, and then it is yellow in a base, and then it's going to be red in acid. So thymolphthalate is going to be blue in base. Am I correct, Akila? Did you see blue when it was in base?
Yes.
Okay, it's colorless at the end point. So it's pretty clear. It's very, very clear when you reach the end point. It's like 1 drop and then it will go end point. Okay, and then when you're in acid, it's just colorless. So it's either colorless going to blue, 1 drop it become blue, or if you have base in your conical flask, the blue, 1 drop of acid, then it will go colorless. That means you reach the end point. So pretty clear there. Same thing with thymol blue and bromophenol blue, if I'm not mistaken, that, these are all going to be blue with base, and then they just turn colorless at the end point there. These are all the indicators as stated in the syllabus. So either of these could come out and you can't blame them really. I mean, it's in the syllabus, okay? So acid-base titration is one of the simplest things you can ever get. I'm just going to go through the other one now. Let's go through the first page, okay? So that was the first question that came out in the paper 3.3. Paper 3.4 is supposed to be a different paper, but sometimes they are similar, sometimes they are not similar. It's as if you cannot predict because it's whatever in the syllabus, all right? The second question that came out in that paper was something called gravimetric analysis. So it's something to do with masses and heating. So you're trying to heat something and then you monitor the change in masses. That's why it's called gravimetric analysis. The third question was a qualitative analysis. So you will always definitely get quantitative analysis. You just don't know which one from the quantitative bits and which one from the qualitative bit. Usually it's around, I would say, give or take, probably 50% of each. So, but sometimes you could get like 15, and then around 10 marks, 11 marks, something like that for the other one. So you have 2 hours for the practical exams. Yeah, I'm just going to go through the rest of the practicals now. Like I said earlier, so feel free to stop me and interrupt me if you got any questions you want to ask straight away. Yeah, these are the list of quantitative analysis practical. Titration, I already shown you between acid and base. It could be weak or strong acid. It could be weak or strong alkali. So this thing, it can be either of them, but all of them would involve the use of indicator because otherwise you cannot see the color change. I don't think I need to remind you on, acid-base titration. You're probably all right with that. The potassium manganese 7 titration. This one is your manganese plus 7. This one is the dark purple color, and it will go to like pale pink or colorless. But if you have a flask, if you have the purple color in the burette, you have your flask. You keep on dropping it, and it will immediately turn like pale pink or colorless. You do not stop. You do not stop when it's colorless. You stop only when one extra drop from the burette and the purple color is not going away. You don't stop when it's purple. You stop when it's permanent pale pink. That is how you know when it's endpoint. Of course, when you did a rough titration, you shouldn't waste your time. You should just try and estimate, in excess roughly, how much in excess. Later on, you try to be careful, and then you do drop by drop until you get a permanent pale pink. If you are ever unsure, stop for a bit, read at the reading first, and then add 1 or 2 more drop, drop by drop, and then stop when you reach the endpoint. You have your previous reading, and now you decide which one is a better endpoint, something like that. Okay. With hydrogen peroxide, shouldn't be that tricky. They are just different reducing agent because this is the oxidizing agent. So this is what we call redox titration. So there's acid-base titration. There's also redox titration, which is between oxidizing agent and reducing agent. Out of all of these, the only one which is very, very difficult is going to be the ethane dioic acid because that is the one that requires heating. I was thinking that it could be one of those things that will come out for the last one, but it didn't. But if it does come out, it's not new in the syllabus. This was from the 2017. So it's not new in the syllabus. It was in the previous syllabus already. It's just that you don't know which one is going to come out. But whatever it is, this is one of the harder practical to do because you do need to heat up the conical flask. The conical flask, before you do the reaction, you need to heat up because negative charge and negative charge ion, they collide because they need to react, but they're going to be very slow to react unless you overcome the activation energy. That's why you need to heat it up. And that is why this is very hard to handle. Easy to say on paper, but when your conical flask is hot, don't hold it with your free hand. Grab a piece of tissue paper, which you'll be given, and then just swirl it around by holding onto the tissue paper. Sometimes people are clumsy in exam, especially practical exams, because it's hot and then they drop the whole thing and then their paper become dirty. So take good care of your paper. If you're doing practical involving this, you must take good care of your paper. Yeah, it's not going to be okay if your paper suddenly becomes stained with KMNO4. The difficult thing with this kind of thing is your calculation because the ratio is not as nice to play with. But as well, I've shown you with the acid and base titration, set up with the label. So it could be the ethane dioic ion. So this is something called ethane dioic acid. As a matter of fact, your paper 2, the one that you did in paper 2.2, contains the ethane dioic acid as a final paper 2 question actually. So this thing here is ethane dioic acid because it's 1 carbon and 2 carbon. It's a dioic acid because it's got 2 carboxylic acid. And then what you get is It is a weak acid because it dissociates partially in solution to give you this conjugate base there. Anyway, the mole ratio from the balance equation is 5:2. Later on, you will do C times V, concentration times volume, but your volume have to be in dm cube, your concentration have to be mole per dm cube. I don't know which one they want you to find, so set up the unknowns and then rearrange your equation, which I hope you'll be able to do. But this was the instruction there. You need to heat it until the temperature is around 70 degrees Celsius. Now, if you are in an actual practical exams, you will just put a thermometer in there. You do not sit around and wait for it to reach 70 degrees Celsius. You just let it be, and then you pipette the next solution so that you will have things ready. When you are going to do the first titration, your rough titration, put the other one to heat. Don't wait around. So this is about planning. If you have never done this practical before, if it comes out, it's really nerve-wracking. I don't know if it's going to come up for the next one, but it is in the syllabus. It could come up anytime. All right. So I hope that is okay. I think the calculations, everything is simple. It's just the heating bit that's a bit tricky. This next one is sodium thiosulfate iodine titrations. I think most people are okay with this. This is also a very common redox titration. If you have starch indicator, the iodine will be blue-black and it will go colorless. One extra drop from the burette, it goes colorless. That's when you know it's the end point. Shouldn't be that bad to do this. But again, the key issue there is your ratio is not in a perfect 1:1 ratio. So the half equation is going to be like this. You have 2 minus. Here you have empirical formula of that. So it's 2 times of that. Minus 2 times 4. Minus 2 times 2 is minus 4. So I need 2 extra electrons there. So this is oxidation, which is loss of electrons. On the other hand, it will react with iodine. Iodine is a molecule which will go to iodide. And then this is reduction, which is gaining of electron is reduction, loss of electrons is oxidation. When you combine these two together, you are going to get 2s2 or 3,2 minus, plus I2 give you s4 or 6,2 minus, plus 2i minus. Now, mole ratio is the kind of thing that I've always been talking about just now. You need to be very careful. Depending on what you want, I really don't know what you want, but most likely it's something to do with the iodine. But it could be the other way around because it's just mathematics. From the balance equation, this is equal. So whatever I have labeled on top is my balance equation mole ratio. And then on the right-hand side, it is what you want and what you have. Which one do you have? Which one do you want? Find the unknowns. Rearrange the equation and find your unknowns. Just keep in mind, this is mole from the balance equation. This is mole from the actual reaction. So this is N equal to C times V, solution and solution. So C times V and C times V. Just make sure your V is going to be in DNQ instead of CNQ there. Okay. Now this is going to be very important. So I'm going to jump the story a little bit because look at this. This is thiosulfate. This is called thiosulfate. So does everyone know that it's called thiosulfate ion? I don't know who do I have here. Akila and Shakira and Iza, and that's pretty much everyone. Does everyone here know what is thiosulfate ion? Have you heard of thiosulfate ion before? Shakira, are you there? Hello, Shakira, are you there?
Hi, sir.
Hi. Have you heard of thiosulfate ion before?
No. Hey.
No. Okay.
No.
All right. Never mind. Akila, have you heard of thiosulfate ion before? Akila, have you heard of thiosulfate? Okay. Rahiman, have you heard of thiosulfate before?
Yes.
And Iza, have you heard of thiosulfate before? Iza, are you there? Okay. Now I need to raise your attention to this thing, yeah? There's a few things in the qualitative analysis that's new, right? You know that if you look at the sample paper 3 for the 2022 syllabus, these are the QA table, right? These are the QA table. Whatever you are used to doing in school, they are most likely based on the old syllabus, unless your teacher has given you the paper 3 syllabus paper. This is for the, sample paper for the 2022 syllabus. So only the sample paper 2022 is based on the new syllabus. So be very careful. So do not assume that the table you have was everything because there is a new syllabus, including the practical. you will see that all of these are the same. So all of these have had no change. So I've noticed that the cation had no change, but there's something in the anions. This is for the 2022 syllabus, yeah? So don't say I don't tell you. This is for the 2022 syllabus. So this is stated in the, if you look up in the sample paper 3, it was published in the year 2019 because they introduced the new syllabus in 2019, 3 years in advance. They tell the teacher, okay, 3 years in advance. So this document was already available online. You should have gone through this in your notes and also in this syllabus for the exam 2022 year onwards. So I don't know, Akila, whether this came out or not, but whenever you add an acid, if you get a bubble, okay, let me give you a scenario, okay? So let's say I have X, it's a solution, aqueous. You don't know what it is, okay? I add acid, I add HCl, and then I get bubbles. What does that tell me if I get bubbles or effervescence? Anyone? What does this tell me? Come on, anyone can answer this? It's easier if anyone answer this.
Gas form.
Okay, gas, all right. So you get a gas. So what is the next thing you should do if you have a gas forming? Are you just going to say test for the gas? So what kind of things react with acid to give you a gas? So what kind of substance react with acid and give you a gas? I can think of two. They are from your year 9 chemistry. What are they?
Hydrogen.
Okay, it could be hydrogen. Is that all? So it could be hydrogen gas. Hydrogen gas is obtained from metal plus acid. Metal plus acid. What else could it be? What else could the gas be?
Chlorine gas.
Chlorine. You can't get chlorine directly from HCl. Okay, you can't get chlorine by reacting acid and by reacting this with HCl. You can't get chlorine straight away unless you are, actually you might be right, it's a redox displacement. So yes, you can get it. Okay, so it will be from a redox displacement. Okay, we'll think about it in a little bit. Okay, what else could give you, gas by reacting with acids?
Carbon dioxide.
It could be carbon dioxide gas. That would be your metal carbonate plus your acid. But we're thinking about getting CO2 by reacting with acid. So this thing has to oxidize the Cl minus to CO2, but we know CO2 is a very good oxidizing agent already from your group 17 chemistry. CO2 is a better oxidizing agent than Br2 than I2. It is unlikely to be the redox displacement reaction. We think about effervescence, a lot of gas could be this or this. Now, when you see this and these bubbles, you would test for either hydrogen or CO2. Which one would you test for first? You see, these are the tests for gas, right? Which one would you test for first if you're in the lab? So you see bubbles by the acid. Which one should you test for first? Hydrogen or carbon dioxide? What do you think, Rahiman?
Hydrogen.
Because that is the easier one to test for rather than this, okay? So if I were you, I would test for this one first. So that would just give a pop sound with a lighter split. So make sure you write down the positive test, then specify the identity. The gas is hydrogen, but then we need to be careful. What have we done here? Acid plus solution. Hydrogen gas is only obtained from acid when acid reacts with metal. Can this be hydrogen gas? What do you think, Rahiman? Can it really be hydrogen gas? Think about what you're reacting. Acid plus solution. Can metal be solution?
No.
No, so there you go. Are you adding a solid? So metal is an element, it's a solid, well, except for liquid mercury, but most metals are solid, right? So most likely we are thinking about carbonate, which of course could be a solid, but there are some carbonate which are given as solution, like sodium carbonate, potassium carbonate, all sodium salts, all potassium salts, all ammonium salts are soluble in water. So it could be ammonium carbonate, could be potassium carbonate, could be sodium carbonate. Okay, hopefully that makes sense, yeah? But you can test for both gas easily. If it is not hydrogen, most likely it will be carbon dioxide. Okay, hopefully that makes sense. And then you would just say you will give a white PPT with lime water due to the formation of calcium carbonate, which is insoluble in water. Now, what else could they ask you to do this? They could ask you to add some, I don't know, what do they do? Add some thiosulfate. So you see, I'm going the other way around. I am not identifying the thiosulfate. I'm identifying, no, that doesn't work. Okay, let me give you another scenario now. So this is Y aqueous. When I add it with magnesium, I get effervescence. You would test for gas, right? You would test for this gas. So metal plus something give you effervescence. Okay, so this something, what could it be? What could Y contain? What can you tell me? How about you, Isa? What could Y contain? So metal plus Y give me effervescence. What could Y contain? What do you think, Isa? Hello, Isa, are you there? Okay, maybe not. Shakira, what do you think? So if I add metal, I get effervescence. What do you think, Shakira? No one? Is the internet a bit lagging? What do you think, Akila, since you did practical already, right? Metal plus something give you effervescence. What do you think Y contains?
Acid.
It could be acid. Could it be anything else? It could be water because, you know, metal plus water. Metal plus water could give you hydrogen gas as well, and metal hydroxide. Metal plus acid could give you metal salt and hydrogen gas. But it's unlikely to be water because you know your theory. Magnesium doesn't react with cold water. Magnesium reacts with steam. So it's unlikely to be cold water because of your O-level chemistry, which you have learned before. Now, you can test for the gas. It is most likely going to be hydrogen gas. So the next thing is, you say that it contains H+, but you don't know what acid it is. You don't know what acid it is. You could test for the anion letter. So you need to test for the anion letter. We know that the common acid would be HCl, which contains Cl-, nitric acid, which contains NO3-, and sulfuric acid, which contains SO4(2-). Each of these is anions that you can test for using this particular table. Test for chloride, test for nitrate, as well as test for sulfate. So you could test for the anion and identify the acid. But what else could they do to confirm the H+? What else could they do to confirm the presence of H+? They can then ask you, add some sodium thiosulfate. Na2H2O3 is Na+, 2 of it, but your key component here is your thiosulfate. Your thiosulfate is H2O3 2-. Thiosulfate will react with acid, and they will give you a white precipitate. It looks a bit yellow actually because it is sulfur. It is sulfur as a solid. Sulfur as a solid is actually yellow, which is insoluble in water. So you get a white precipitate forming as thiosulfate reacts with acid. Yes, it gives you a white precipitate, kind of looks a bit yellow, but we write it as white precipitate. But this is very slow. So they could ask you to leave the reaction, leave it to stand. Leave it to stand for like a minute or two. And then later on, you will come back to read it, and then you get a precipitate with thiosulfate. So that means it must contain H+ because it reacts with H+. So what I've done is I've reversed the scenario. I have reversed the scenario a little bit so that you are not just identifying the thiosulfate, but you are also identifying the presence of the acid as well by reacting with thiosulfate. Okay, hopefully that makes sense, yeah? Now, what is the next thing that's very important then? The reason I talk about this is because that precipitation is a very common reaction with rate of reaction. Have you done the disappearing cross experiment? This is under rate of reaction. You see this? And you mix reagents, and then you sodium thiosulfate and an acid. They don't say which acid because it will work with any acid. And then how much time is required for the precipitate to be produced? This is actually the sulfur precipitate, the one that you mentioned just now. A white precipitate forms when acid reacts with thiosulfate. So this is your disappearing cross experiment. Can I just ask everyone, has everyone here done this before, disappearing cross experiments? Have you done it before, Shakira?
No.
Okay. Rahiman, have you done this before?
No.
Iza, have you done this before?
Yes.
And Akila, have you done this before?
Yes.
Okay, it's practical, yeah. So it's not that bad. Okay, with any practical, don't be scared if it's something you have not done before. So this is just from one of my former students. It's okay. So as you do the practical, you will follow the instruction. So you would have the conical flask, and then you have, I think this thing is an insert. So this thing will be provided by Cambridge. So in school, usually we just draw a big cross at the bottom. We just draw a big cross at the bottom. But if it is provided by Cambridge, they will give you like a bunch of words. Doesn't matter. You just put the thing on top, the conical flask on top of the paper. You look from the top. You don't look from the side. You look from the top. Follow all the instructions. Usually it involves mixing two things together. You mix the thiosulfate ions and you mix the acid together, and you will get sulfur precipitate. So it will become cloudy, and then the words will disappear. That's what it's saying. Stir the mixture once. So you got to read the question. Yeah? Sometimes they ask you to stir it continuously. But do you think the reaction will be faster or slower if I stir continuously? What do you think, Rahiman? Faster or slower if I keep on stirring the reaction?
Faster.
And can you think about this, everyone, in terms of collision frequency? If you collide them, if you stir or swirl it continuously, you will make the particles collide more frequently, and you will change the rate, and your experimental result will be different from the supervisor, because your supervisor or your center supervisor who will do the practical will follow the instructions, and then they will just stir once. So follow your instruction. Practical is all about following instruction. So make sure you can read, circle and underline instructions so that you don't make any mistakes at all. Yeah. Sometimes they do say start timing immediately, stop timing when it becomes invisible. Now this is decision. So your decision is going to be slightly different from other people, but it shouldn't be too different. Okay. So you have your stopwatch. You start timing when you mix them, and then you look from the top. Okay. It's not going to happen in like 5 seconds. Sometimes usually it takes, I don't know, it depends. Like you said, like I've shown you with the qualitative analysis, after a while, slowly, okay? But it wouldn't be like 10 minutes. It would be like shorter than that, because it's a practical that's bound to work in a practical exam kind of setting. So you would just stop timing when it becomes invisible. That means when it becomes opaque, so you cannot see it anymore. Don't look from the side. When you look from the side, it's slightly different from when you look from the top. So look from the top, okay? When you rinse everything, make sure you rinse you rinse everything with distilled water as well, yeah, at the end. And you're gonna add now 40 cm of Fa3. Just now you used 40 cm of Fa3. So what are we changing and what are we not changing? This is also important in your paper 5 as well. So when you read the question, how does the rate changes by the concentration of the acid? So looking at this is what you change. You are trying to change the concentration of the acid. I'm sure in biology you have learned this as some sort of variable. Do you call this independent or dependent variable? What do you think is that? If you are there, the rest of you try and think about this as well. So what you change in the experiment, is that dependent or is that independent variable? Are you there, Isa?
Dependent.
Dependent. Do you agree with her, Akila? Is that dependent variable or is that independent variable, Akila?
Independent.
Okay, I asked one more person because we had a contrasting answer, right? What do you think, Shakira? What you change in the experiment, is that dependent or independent? Or you don't know?
Independent.
What you change is called independent variable, okay? So there is something that I always try and remember. It's what my old biology colleague used to tell me. The y-axis is what you measure, right? The y-axis is what you measure, and the x-axis is what you change. You change on the x-axis, and then you will measure on the y-axis. So what you measure, y, are you so dependent? So that is how I always remember dependent variable is on the y-axis. Dependent variable is what you measure, which means independent variable is what you change. Okay, so as you change independent, then the dependent variable, what you measure, will be different. Now look at the experiment. You wanted the rate of reaction. Okay, you wanted the rate of reaction. So rate of reaction is on your y-axis, but in reality, you are not measuring the rate of reaction, you are calculating rate of reaction. What are you measuring? So when the question asks you, what are you measuring? It is not going to be rate of reaction. So what do you measure then in this experiment? What do you think, Rahiman? What do you measure in this experiment?
Time.
Time, okay. So time is actually your dependent variable. So this is time for the precipitate to appear, or for your writing to become invisible. So it's the time for that reaction. Okay. So this is what you measure. So this is dependent variable. Okay. So what else could affect rate of reaction? This is about rate of reaction. There are other factors which can affect rate of reactions. Oh yeah, okay, I got your message, Akira, it's all right. There are other factors that can affect rate of reaction, but then we don't change them. We don't change them because we are just changing the concentration of acid. We cannot change too many things at one time. So there are other factors which can affect what we are trying to investigate, but we don't want them to change. Do not change. We keep them constant. So what kind of terms do we call this type of variable? It's not dependent, it's not independent. Do you know what you call this, Iza? Probably not. Do you know what you call this, Rahiman? So we keep this other factor constant. What do we call this variable as?
Is it control?
It is control variable. In every experiment, these are what you call to have a fair test. Fair testing means you mix the other control variable. You must have some things called control variables because these are things that can affect what you're trying to measure. What you're trying to measure is rate, and you're trying to change concentration of acid. So what do you think are other factors that could affect rate of reactions that you want to control in this experiment? Why don't you suggest one or two, Rahiman? What do you need to keep constant?
Temperature.
Temperature is the most obvious thing because we are not trying to change temperature. We are trying to change concentrations. So temperature is very obvious. So you don't want to change temperature. You want to keep the temperature constant. What else do you want to keep constant? You are trying to investigate the effect of changing concentration of acid. So do you want to change the concentration of the thiosulfate in these experiments? What do you think?
No.
So in this experiment, because this is what you're trying to change, you must keep this S2O3 2 minus, which is Fa3. This is Fa3. So you want Fa4 to change. You want Fa3 to remain constant because you're not trying to investigate what happened to Fa3. So keep the volume, keep the concentrations of Fa3 the same. And that is the reason why Fa3 40 cm cube, Fa3 40 cm cube, Fa3 40 cm cube, because we are not changing that. What are we changing? We are changing the concentrations of your acid, which of course then you see 10 cm cube of Fa4, this is your acid, and then you have 20 cm cube of water. We have 10 cm cube of water, and then 20 cm cube of Fa4. So if I have a table, this will be volume of Fa4, volume of Fa4. This is the acid, and then this will be the volume of H2O together with the unit. So I have experiment 1, 2, and 3. In experiment 3, I have 20 cm cube of distilled water, 10 cm cube Fa4, 20 cm cube Fa4, 10 cm cube that, and I have 30 cm cube Fa4, and I have 0 cm cube water. Am I correct? Yeah, 0 cm cube water. As you can see, you are diluting the acid because the acid, there's lesser of it, but there's more water. But if you see, the total volume remain constant. This is important because you're doing a dilution where you're doing C1V1 equal to C2V2. So you're saying that if we have lesser of the concentrated stuff, okay, so lesser volume of that means the concentration of this is going to drop down when you have a greater total volume at the end. You're going from here to here. So if you have 10 cm cube of the Fa4, now you have 30 cm cube diluted Fa4. So this is going to be less concentrated than this because you have just added water. it becomes diluted. Hopefully you can understand the idea of dilution there. Yeah? The actual experiment is not bad. This student lost marks because to the nearest second, always read instructions, etc., etc. Also, always read instructions. The rate is calculated, not necessarily 1/time, but here's 1000/time. Make sure you score these kind of things. This is just about the dilution here. So obviously, as you can see, they become more dilute. So you should be able to do this kind of calculation. Well, this is just basically what happened to the rate as the concentration changes. Of course, you'll be able to explain it in terms of collision frequency. This is your O-level rate of reactions. As your concentration decreases, there will be lesser particles per unit volume because mole per dm cube. So less particles per dm cube, they will collide less frequently, and therefore rate of reaction is going to be slower. And then the next one is about concentration. H2SO4 will give you 2H plus SO4 2 minus. When you have HCl, that gives you 1H plus S plus Cl minus. Of course, then we are talking about 0.20 molar H2SO4 and 0.20 molar HCl. So we will get more H plus per unit volume, therefore rate is going to be faster. This one is a very popular question. I'm not saying that this will come out. Yeah? I have no idea what's going to come out. Okay, this is just one of those things because you guys haven't done this before. I thought it's quite nice to go through this. Yeah, okay. This is saying if you use bigger versus smaller, is your cross going to disappear faster or slower? That's the question. If you use bigger beaker versus smaller beaker, you are changing the size of the beaker, but you're not changing the volume of solution. So the volume of solutions is still the same. So if this is the smaller beaker versus the bigger beaker, okay, you think about the same volume of solutions, where would they be? Because this is smaller, it will go higher. Because this is a bigger beaker, it's going to be lower in level. I hope everyone can see that because you have a bigger surface area like this, right? Okay. So when you have a deeper, this is called deeper. So the depth of solutions is higher. So it is deeper depth of solutions. It's going to be much harder for you to see when it becomes insoluble. Okay. When it becomes how do I say this? Am I correct? Let me see. What does it say? Bigger beaker, the reaction time will be slower. So the reaction time will be slower. I agree with this second bit. And then it is saying that because it's not deep enough, you want it to be fully invisible to reach the endpoints. Well, I hope you get the drift. I mean, the idea is that when you change the depth of the solutions, okay, you are going to have a different time at which you will see the precipitate disappearing. So think about it, and hopefully you'll be able to do this kind of things easily. Yeah. Now this is about uncertainty. Okay, I need to talk to you a little bit about percentage error. You see how to do this percentage uncertainty is called percentage error. This is percentage error in time. When you calculate time, you started from 0, you click your stopwatch, you started from 0, 0, 0, everything. But whenever you read the time, you do not take away, you do not subtract the initial time because it started from 0, right? So you do not subtract the time. So only one reading required. You never subtract the 0.00, right? Okay, so only one reading required, which is why if this is the uncertainty, there is no multiply by 2, it's just on its own, divided by the reading times 100%, and you will get 4.1%. The same thing for this, only one reading. That is because when you are dealing with time, time is one of those things you only do once. You only do once. You should probably take note of these. Okay, I'm going to talk a little bit about error. So what is to do with errors? This is called percentage error or percentage uncertainty. Okay, couple of things. There is the volume of pipette. When you take something out from the pipette, your pipette is 25.0 cm cube in the school laboratory most of the time. You do it one time. Because when you reach the mark there, You don't take away minus 0.0. No, you don't. You just do it one time for your volume of pipette. So you never multiply by 2. Okay, just like time. You never multiply by 2 because you only take them one time. Okay, so these are the 2 readings which you do not multiply the uncertainty by 2 because you only need 1 reading. Every other reading, you kind of need to multiply by 2 because when you are dealing with masses, so you use a mass balance. So a mass balance or electronic balance, you will have initial mass and you will have final mass. Then people say, okay, but I start from 0.00, but I start from 0.00. How do you get 0.00 in the first place? You press the 0 or the T button. When you press the 0 or the T button, you are saying take away from whatever mass I have. That is what it means. When you press the 0 or the T button, it's called tearing. And that is what you do with the mass balance, right? You press it. That means take away from 0.00. So you're essentially doing the final minus the initial mass already. That's why you will have 2 readings there. If you think about your mass balance, which in the lab measures the 2 decimal place as required by the syllabus, so you have 0.00. The next reading you see on the balance on the display will be like this. So your smallest division, they call it the graduations. So the smallest divisions, or they call it the graduation, graduations. That means the difference between the intervals, it's going to be 0.01 gram. So your error in a single reading. So when you read the initial mass, what is going to be the error? When you read the final mass, what is going to be the error? It's going to be the smallest division divided by 2, so that will give you 0.005 gram. In mathematics, in lower secondary mathematics, you will have learned of upper bound and lower bound, and this is the smallest division divided by 2. Okay, I hope everyone knows how to get the error in a single reading. This single reading is for the initial mass, is for the final mass. So this one, you will have a reading, it has this much error. This reading has this much error. So when you want to calculate the mass, that is going to be the final minus the initial. So you do need 2 readings. And as a result of 2 readings, what is the error in the mass? What is the percentage error in your mass? That is going to be plus minus 0.005 multiplied by 2 divided by your mass. And they want the percentage error. So you have to multiply that whole thing by 100%. The idea there is you have to multiply by 2 because you involve 2 readings to get to this mass value there. Of course, then you could have thermometric. Thermometric means something to do with heat. So these are thermometric experiments. These are to do with temperature. Your temperature is measured with thermometer. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, like that. So your thermometer goes up like that. So if this is 10, this is 20. So you will see the smallest division. This is 10, and then this will be 11, etc., etc. So what it means is the smallest division is 1 degree Celsius. But then what is the error in a single reading? So I'm going to ask one of you now, what is the error in a single reading on your thermometer that you use in the laboratory? These are sometimes 1 or 2 marks, right? Okay. So what do you get, Akila? What is the error in a single reading on thermometer? Yes, Akila. So the smallest division is 1 degree Celsius. What is the error when you read 1 temperature on the thermometer, Akila?
0.5.
0.5. And how you get that is the smallest division divided by 2. Now, when you have initial temperature, when you have final temperature, that's what you do in experiments. And then you say delta T is your change in temperature, final minus initial. Your final temperature has plus minus 0.5 degrees Celsius. Your initial temperature has plus minus 0.5 degrees Celsius. The percentage error in delta T is going to be your error in a single reading multiplied by 2 divided by your delta T times 100%. Okay, hopefully everyone is okay. Now this is to do with percentage error. Okay, so when you do Q equal to MC delta T, and then Q, you can work out delta H equal to minus Q over the mole of the limiting reactant. Now, they will ask you, what makes the experiment not accurate? How to make it more accurate? How to make experiment more accurate. So one of the obvious thing that you can think about will be heat loss. So you need to reduce heat loss. So you can use a plastic lid to cover your plastic cup. You can insulate outside the plastic cup, that kind of stuff. You can repeat the experiments so that you get 2 readings for each experiment, and you can average out the reading. Or one thing is, I'm going to ask you in terms of percentage error then. Sometimes the question asks you percentage error, then they ask you what will happen if delta T is bigger, if delta T is smaller. Okay. Now, if delta T is small, what will happen to the percentage error in delta T? Is it bigger or is it smaller? What do you think, Shakira? If the change in temperature is small, what happens to percentage error in the change in temperature? Is it bigger or smaller?
Smaller.
So the thing at the bottom is smaller. Something divided by smaller, is it going to be bigger or is it going to be smaller?
Bigger.
There you go. So we just need to think about, it's not on top, it's the denominator. 1/1 is 1, 1/2 is 0.5, 1/3 is 0.33. As we increase denominator, the delta T increases, the percentage error increases. Is your experiment going to be more accurate or less accurate, Shakira, if your percentage error increases?
Less accurate.
Yep. So to improve accuracy, you don't want your delta T to be very small. So sometimes they can ask you, explain why this experiment is very inaccurate. Maybe because the delta T is very small. So typically the exothermic or endothermic reaction in the lab is probably an increase of 10, increase of 20. If you increase by 0.5 degrees Celsius, you don't know whether there's experimental errors or whether there is an actual thing manifest from the experiment. Yeah, I hope you understand that. Now, if you go back to mass, so people say, oh, I don't want to waste chemicals, so I can use 0.02 gram versus 0.20 gram. Okay, I can use this as the mass of the solid I'm going to react. Which one is going to give me a bigger percentage error in mass? 0.02 or 0.20? What do you think, Rahima?
0.02.
So this one, because it is a smaller mass, would mean, of course, you can show this formula, okay? So higher percentage error in mass, so less accurate. So one of the popular questions involve making up a solution. Have you heard of make up a solution before? Who have never heard of making up a solution before? When you have a solid, and then you put inside a beaker, and then you add distilled water, and then you stir. Okay, and then after that, you pour into a volumetric flask. When you pour into a volumetric flask, it is not full yet. What you do is you need to wash. You need to wash the beaker. The reason of washing the beaker is to dissolve any residual solid, because you might have some solid which was insoluble, and then you redissolve again in a small amount of water, and then you will combine the washing. And then combine whatever you dissolve extra amount with extra amount of distilled water, and then you will top it up. You top up with distilled water, because we don't use any kind of water. We top up with distilled water until the 250.0 cm³ mark. And after that, you need to stopper. After you stopper, you need to mix, shake, so that we get a uniform concentration. Just like when you make a syrup solution, you want the concentration to be the same throughout and not just concentrated at the bottom and just allow water on top. Okay, can I just double check, has everyone done something like this in the lab before? Has anyone never done something like this in the lab? So everyone is all good? Okay, so this is quite common. Sometimes they ask you to have a mixture, and then they ask you to react with excess acid, and then you could have some remaining solid remaining. So the idea really is, the overall idea is, the solid becomes solution. So you just add distilled water. You just add distilled water. So the overall concept is quite simple in the sense that This is mole equal to mass over mR. This is a solution. So in your solutions, you have mole equal to concentration times volume. Because you're just adding distilled water, I draw a simple diagram. I can see all of these goes into that. Nothing has escaped, nothing has been added. I just add distilled water. Solid becomes solution. So that means mass over mR equal to C times V. I can relate that. What is the purpose of doing this? When I make up a solution, I can take out. I can take out for titration. But when I use it for titration, I don't use all 250 cm cube. Instead, I will use 25.0 cm cube for titration. So here, this will be 250 cm cube. From here to here, this is taken from the same solution that you have prepared. So here, the concentration is the same. The concentration is the same, but the mole is different. Whereas here, the mole is the same. We don't have concentration for the solid, but the mole is the same. The concentration is the same. If the concentration is the same, and N equal to C times V, concentration is the same, lesser volume means lesser mole. So when you work backwards, if you have to work backward, because this is where you start in your practical, so you will do some titrations, and then when you work backwards, so if you have the mole here, if the mole here equal to X, therefore the mole here is going to be much, much bigger because you have bigger volume, but you have the same concentration. You take it from the same bottle. So it's going to be 250 over 25 times X, which is 10 times X. And we know this is the mole of the solutions, which is here, and this is equal to mass over mR from the solid, and that is how we can do this kind of questions. It is called backward titration. So you need to know your basic mole formula, you need to be okay with units, and you need to draw a few diagrams so that you can see what is changing and what is not changing. Very, very important that you keep your head straight, what is changing and what is not changing. Simple, lousy diagram like this would have helped you because they would allow you to visualize what is actually happening. Okay, so I want to go back to the actual syllabus and see what else did I miss out on. Gravimetric analysis. So this was what came out in paper 3.3. I think Akila did the practical. I think the rest of you haven't done the practical. I saw Afif. Afif has just joined our Zoom. Afif, have you set for the practical yet?
Not yet.
Oh, it seems like everyone else hasn't set for the practical. Okay, so I'm just gonna. I have the rest of these full review on my YouTube channel. Yeah. Okay. So you can go through whatever I didn't manage to go through. This is an example of like copper 2 sulfate hydrated. So you are provided with this hydrated copper 2 sulfate. As usual, wear a crucible. We use a crucible because we need to heat it. This is called gravimetric analysis. So if they ask you to weigh with a lid, you weigh with a lid. If they don't ask you to weigh with a lid, don't put in the lid. So you will level. Make sure you have units. Units are one of those things that you will get the marks on. And make sure it's 2 decimal place because on your mass balance, they will measure 2 decimal place. Let me tell you something very funny, okay? So this is mass of crucible. This is mass of crucible plus FD1. So here, by right, I should write in mass of FD1 used, but because that was just what they asked us to write down, it's actually here where they asked us to calculate the mass of FD1 used, okay? So this student has taken this minus this. This is how much FD1 was used. This is the hydrated because before you heat it, it still has water of crystallization. After you heat it, it has lost the water of crystallization. You heat it to constant mass. This is what we call heat to constant mass. Heat until mass is not changing. Why do you heat until mass is not changing? Because so that there is no more water that is given out, so that there is no more water to be lost. That is when you know everything becomes anhydrous already. This is called anhydrous because no water crystallizations. This is just your mass of CuSO4. This is the mass of CuSO4 dot XH2O. So from here, this, am I correct? This doesn't seem very good. What am I doing here? This doesn't seem very good. I must have done something wrong. 24.77 is without water crystallization. This is with water crystallization. I think I've got it the other way around, which means my video was wrong actually. This is the mass of water used. This is going to be the mass of the solid. the mass of the hydrated solid. Hydrated solid, am I correct? 24.77 minus 23.09. No, this is the mass of the anhydrous solid, that is correct. Because they have taken 24.77 without any water, minus the crucible, this is just the mass of CuSO4. The top one there is just the mass of the water. The whole idea of these questions was basically gravimetric analysis. I think this was not what came out in the paper 3.3, but the idea is going to be the same. As long as it's gravimetric, you compare masses, and then because you have CuSO4, is to X mole. So 1 mole of CuSO4 is to X mole of H2O. So the mole of H2O is to the mole of CuSO4 equal to X over 1. This is your mole, mass over MR from your previous BIBD experiment. Gravimetric is probably one of those things that you can hopefully hope for in your practical. It's one of the easiest things to do, but make sure that water crystallization is going to be a whole number. Okay, I don't have much time, but let me just very quickly tell you gas volume collection. Okay, gas volume collection is definitely an important one as well. If you have never done this, if you have never seen this before, please watch the video. Okay. This is on gas collection. If this comes out and you've never done it before, you are quite screwed in the exam. Okay. I believe all of you have done thermometric, something to do with MC delta T, record the temperature rise. So I don't have time to go through all of these, but your exam is on 31st. I'll probably see you next week again, so I can continue more of these, but you can watch the rest of the video actually for that. So I will see you guys next week. But please make sure you watch how to collect gases. That's very, very important if you've never done it ever before. I know it's COVID time last year, but you have a practical exam. So if you've never done it before, try to think about how to do it. And it's around half an hour video for these, So if you want, you can watch it. If not, then I will go through some of these next week. But I think it's best if you actually go through yourself first. Okay. I think better if we just all turn on our video for a little bit and let's just take a quick group photo before I let you go. Otherwise, yeah. All right, so that's it really. But let's just turn on our video for a little bit. Oh no, people has left. Okay, never mind. Never mind then. Don't worry. Just leave. Just go to your next session. Okay. All right, I'll see you guys next week then. Bye-bye.
Yes, sir.
Okay, bye-bye.